Intermediate Algebra for Statistics, Exponential Functions, Part 3. Lesson objective: use 2 points to find an equation of an exponential function. We'll begin with an example. Example 10. Find an approximate equation y equals a times b to the x power of a exponential curve that contains the points 0, 3 and 4, 70. Round the value of b to 2 decimal places. Solution? Well, first we're given the y-intercept. 0, 3 means that the y-intercept is 3 because it is the value of y when x is 0. That means that our value of a is 3. So now we have y equals 3 times b to the x power. All we need to do now is find the value of b, the base. So we're going to use this point here, 4, 70. When x is 4, y is 70. So substituting those values in for x and y, we can solve for b. So we have an equation that only has one variable, b. So solving for b, we need to get rid of the 3 and we need to get rid of the power of 4. Dividing by 3 first, we get 4b equals 70 divided by 3. Take the fourth root of 70 divided by 3 and add our plus or minus. We have the solution b equals plus or minus 2.20. Now, because exponential functions, the base is always positive, we only need to write down the positive solution, 2.20. An exponential function, the base cannot be negative. So we have our equation, y equals 3 times 2.20 raised to the x power. So this graph contains a 0, 3. It doesn't exactly go through 4, 70, but it's close. And the reason why it doesn't is because we are rounding b to 2 decimal places. Lesson objective: property. If a equals b and c equals d, then the equation a divided by c equals b divided by d. In words, the quotient of the left sides of two equations is equal to the quotient of the right sides. Now let's look at an illustration. Let's let a be equal to 5 and c be equal to negative 4. Then b also equals 5 because a and b are equal, and d equals negative 4 because c and d are equal. So if we plug these values in for this equation, we have 5 divided by negative 4 equals 5 divided by negative 4. So it works. The left-hand side equals the right-hand side. So you may ask, why do we need this? Well, let's look at an example and we'll see. Example 11. Find the approximate equation y equals a times b to the x power of the exponential curve that contains 2, 5 and 5, 63. Round the values of a and b to 2 decimal places. Unlike example 10, where we're given the y-intercept, we're given 2 points and we don't know what the y-intercept is. We have to find it. So solution: since both points must satisfy the equation, we have 2 different equations. We need 2 equations because we have 2 unknowns. We don't know a and we don't know b. So if we substitute 2 for x, that will be equal to y. And for the other point, when x is 5, y is 63. Now this will be easier if we put the largest y value first and then the smallest. Now why do we do this? It's because now we are going to apply that property where we divide these 2 equations. So this system is equal to this. 63 divided by 5 is equal to ab to the 5th power divided by ab squared. Now next, the a's will cancel, and then we have b to the 5th divided by b squared, and these bases are the same, so that means we subtract the exponents. And we have b to the 3rd equals 63 divided by 5. Now taking the cube root of 63 over 5, we have b is approximately equal to 2.33. So we found our first variable, b. But now we have to find a. So we put b in, we pick a point, it doesn't matter which point. I'm going to use 2, 5. 2 goes in for the x, we have our value of b, and y is 5. Next, we want to square. So next, we want to solve for a, so this value is multiplying the a, so we divide, and we have a is equal to 5 divided by 2.33 squared. Evaluating this, we have a is approximately equal to 0.92. So our equation is y equals 0.92 times 2.33 to the x power. They should come close to these points. So to verify this using the graphing calculator, we put the equation in y1, we hit graph, and then we can use our trace feature for the 2 points. Summary: we can find an equation of an exponential function using the base multiplier property or by using 2 points. Both methods give the same result. Example 12. Find the equation y equals a times b to the x power of the exponential curve at the right. So let's zoom in where we can see some more values. It looks like the y-intercept is 1, it's hard to tell. But if we look carefully for sure, we see when x is negative 1, y is 4. And the reason why it's 4 is because our scale here is 2. Here's 2, 4, 6, 8, 10. So we have 1 point. When x is negative 1, y is 4. The next one, when x is a negative 2, y is 16. So we have 2 points. When x is negative 1, y is 4. And when x is negative 2, y is 16. So we have our 2 points. Now we can answer this problem just like we did in the previous problem. We have 2 points, so we need 2 equations. The first equation will be 4 equals a times b to the negative 1 power. So this was our first point. X is negative 1, y is 4. And the second point, and the second equation, 16 equals a times b to the negative 2 power. X is negative 2, y is 16. So taking the largest y value, putting it on top, the second equation on the bottom, dividing the left-hand sides, the right-hand sides. We have 16 divided by 4, which is 4. The a's will cancel, and now we have b to the negative 2 power divided by b to the first power. Since b's are like terms, we subtract the exponents, and we have 4 equals b to the negative 1 power. To make a negative exponent positive, and since it's in the denominator, we send it to the numerator, and 4 is the same thing as 4 over 1. Solving this equation, one way of doing this is to cross multiply. 4 times b equals 1 times 1. Dividing by 4, we see that b is 1/4. To find a, we substitute the value in for b. We pick a point. I'm using the first point. X is negative 1, y is 4. Using our properties of exponents, this becomes 1 to the negative 1 power, 4 to the negative 1 power. So the 1 will be sent to the denominator, the 4 will be sent to the numerator. So this becomes 4 over 1, and 4 over 1 is 4. We multiply that by a, we have 4a. So 4a equals 4. Dividing by 4, we see that a is equal to 1. So our equation is f of x equals 1/4 to the x power. It appeared on the graph that the y-intercept was 1, and now we know that's true. And it would have been easier to solve this problem if we knew the y-intercept was actually 1. Because in that case, we have our value of a, We only need one more point to find b, and -1, 4 will work. And plugging in those values, we get 4 equals b to the -1 power, which means b is the 1/4. And we end up with the same equation. So we can find the y-intercept from a graph. It makes the work a lot easier. So let's summarize exponential functions algebraically, numerically, and graphically. Algebraically, it's written in this form: f of x equals a times b to the x power. A is our y-intercept, b is our base, and if b is between 0 and 1, it'll be a decreasing function. If a is positive, a is negative, it'll be an increasing function. If b is bigger than 1, it's an increasing function. If a is positive, if a is negative, it's a decreasing function. But the base b cannot be negative. Numerically, as x increases by 1, the y values are multiplied by the base value. The value of a is the y-intercept. And graphically, exponential functions look like this or this. This is an example of an increasing exponential called a growth. And this is an example of a decreasing exponential, and this is called an exponential decay. Thanks for watching.